Hi and welcome to my channel. In this video we will look at a VPN community here, community options. So the first one we encounter here is encrypted traffic. This page allows you to define how traffic between the security gateways, the center and satellite is encrypted in a VPN community. The options here accept all encrypted traffic on. Choose this if you want all traffic between the participating gateways to be encrypted by default. And here we can, if we enable this, we have two options: satellite gateways only and both center and satellite gateways. So both center and satellite gateways, this ensures that all traffic between the center gateway and the satellite gateways is encrypted. And satellite gateways only, only traffic between satellite gateways is encrypted, leaving non-satellite traffic unaffected. So let's move to the next option here. Okay, encryption settings. Here we can see that we have options for phase 1 and phase 2. When configuring a VPN in Check Point, you need to define the encryption method for the Internet Key Exchange or IKE protocol. This determines how the VPN establishes secure tunnels between gateways. So here we can see directly under encryption method we have three different options: prefer IKE v2, support IKE v1, IKE v2 only, IKE v1 for IPv4 and IKE v2 for IPv6 only. So let's talk about IKE v2 only. The VPN will exclusively use IKE v2 or version 2 for negotiation and encryption. A limitation here is that this option is incompatible with gateways or peers that only support IKE version 1. And the IKE v2 is best for modern environments where all gateways support IKE v2. The next option here is the prefer IKE v2, support IKE v1. This is the recommended one. The security gateway prioritizes IKE v2 when peer also supports it. If the peer only supports IKE v1, the gateway fails back to the IKE 1. Best for mixed environments with a mix of older and newer gateways. This ensures compatibility without sacrificing IKE v2's advanced features when available. And then here, when IKE 1 only, the VPN will exclusively use IKE version 1 for encryption. Limitation: modern features of IKE v2 such as faster negotiation and better performance will be not available. Best for legacy environments where IKE v2 is not supported. Practical notes here. So IKE v version 2 benefits. IKE version 2 offers faster connection setup, improved resilience during disconnections, and stronger security algorithms compared to IKE version 1. The recommended setting: use prefer IKE v2, support IKE v1 to balance compatibility and performance. So this is the recommended option. So now let's take a look at the phase 1. The purpose is to establish a secure and authenticated channel between two devices by negotiating security parameters. The first option here is the encryption algorithm. This defines how the data exchange during the negotiation will be encrypted to ensure confidentiality. Common algorithms include like DES, 3DES. So the DES is outdated, insecure, and it is not recommended at all. The triple DES, stronger but slower. And we have ACE 128, ACE 192, and ACE 256. and these are the used in the modern deployments. And then let's move to data integrity here. This ensures that the data has not been altered during transmission. Common algorithms include MD5, which has vulnerabilities. Do not use MD5. SHA-1, secure hash algorithm, stronger than MD5 but outdated. And we have SHA-256, SHA-384, SHA-512. Secure hash algorithm 2, preferred for modern deployments. So now let's take a look at Diffie-Hellman group. This determines the strength of the key exchange mechanism used to derive shared secret keys. Higher group numbers provide better security but require more processing power. So if we choose group 20, it's more secure, but it will make your CPU hot. Common groups are group 1, insecure and outdated. Group 2 is minimum recommended. Group 5, 1536, better security. Group 14, widely used and secure. So the recommended one here is group 14. But as I said, this will make the CPU more hotter, or the CPU will be more used. Let's take a look at the IKE version 1 phase 1 modes. We have main mode, which is more secure negotiations in 6 exchanges, and aggressive mode, faster, only 3 exchanges but less secure. And here, if you click on advanced here we can use the aggressive mode. So if we check this, we can use the aggressive mode. So now let's take a look at phase 2. IKE phase 2, also called the IPsec phase. The purpose is to negotiate parameters for protecting actual data traffic. This includes defining the encryption, data integrity, and optionally using perfect forward secrecy, the PFS. So first, let's take a look at the encryption algorithm. This defines how the actual data payload is encrypted. Common encryption algorithms for phase 2 include ACE 128, ACE 192, and ACE 256. 3DES, still used but slower and less secure. DES, outdated, not recommended at all. So if we change, for example, to like this, we can now define data integrity. This ensures that transmitted data has not been tampered. Common integrity algorithms are SHA-1, secure hash algorithm but outdated, but still in use in legacy systems. SHA-256, SHA-384, or SHA-512. So you can see that we have do not use MD5. So not recommended due to vulnerabilities. And now let's take a look at the PFS, the perfect forward secrecy here. So check this. What is PFS? So perfect forward secrecy ensures that if one key is compromised, past sessions cannot be decrypted because keys are regenerated for each session. This adds a layer of security but slightly increases computational overhead, so CPU usage. How is PFS implemented? PFS uses a new Diffie-Hellman key exchange during phase 2. Common Diffie-Hellman groups for PFS includes, so we can look here, almost the same, and the group 14 is the recommended one. And then here we can take a look at override encryption settings for externally managed gateways. This is a granular encryption for externally managed gateways. When you add an externally managed VPN gateway to a VPN community, the externally managed VPN gateway may use a different encryption suite than the VPN community. With granular encryption, you can add an externally managed gateway that uses a different encryption suite to participate in an existing community without the need to change the encryption methods in use or split the VPN community. So now let's jump to the tunnel management here. Permanent tunnels in VPN communities. Each VPN tunnel within a community can be configured as a permanent tunnel. These tunnels are continuously monitored, and if a tunnel goes down, a log entry alert or user-defined action can be triggered. Monitoring is achieved by periodically sending tunnel test packets. As long as responses are received, the tunnel is considered up. If no response is received within a specified time frame, the tunnel is deemed down. Permanent tunnels are only supported between checkpoint security gateways. So no third party, we cannot use permanent tunnel with a third party firewall or VPN device. And these are configured at the community level. The configuration options include, as we can see here, if we enable this, we have all tunnels in the community, on all tunnels of specific gateways, on specific tunnels in the community. So the entire community, configure all VPN tunnels within the community as permanent. Specific security gateway, set specific security gateways to use permanent tunnels. An individual VPN tunnel, define specific VPN tunnels between selected security gateways as permanent. And here we can see route injection mechanism. This RIM or route injection mechanism allows a security gateway to utilize dynamic routing protocols to distribute the encryption domain of a VPN peer security gateway to the internal network. So when a VPN tunnel is established, RIM automatically updates the local routing table of the security gateway to include the encryption domain of the VPN peer. RIM can only be enabled if permanent tunnels are configured for the VPN community. And now let's take a look at the VPN tunnel sharing here. One VPN tunnel per each pair of hosts. So the first option here creates a separate VPN tunnel for each pair of communicating hosts, source and destination. What is the use case? When strict security is required and granular control is needed for each host-to-host communication, suitable for environments where detailed logging and monitoring of specific host communications are important. Common in scenarios with high security applications or where compliance mandates strict segregation of traffic. The second option is one VPN tunnel per subnet pair. This establishes a single VPN tunnel for all communication between two subnets. The use case, when multiple devices within two subnets need to communicate securely without creating excessive tunnels. Balances performance and scalability while maintaining subnet level separation. Suitable for medium-scale deployments where scalability and simplicity are prioritized over host-level granularity. And the last one is one VPN tunnel per gateway pair. This is uses a single VPN tunnel to handle all traffic between two security gateways, regardless of the subnets or hosts involved. The use case, this is ideal for large-scale environments requiring maximum scalability and minimal overhead. suitable for scenarios where inter-site communication involves many hosts or subnets, and peer hosts or peer per subnet segregation isn't necessary. Common in hub and spoke or site-to-site VPN configurations where efficiency is critical. So let's cut this video here, and we will continue this discussion on the next video. So thank you for watching, and see you in the next video.